So we were discussing the spectrum of a jittery clock, where we have the ideal clock, 50% duty cycle and a period of T naught. And a real clock whose edges are displaced from the ideal ones by some amounts, which I will call, which I will denote as a discrete time signal. Okay. So the error between these two consists of pulses which have an amplitude of 2 times Vp, where Vp is the peak value of the signal. And so on. And the width of these pulses is the jitter at that instant. Okay. We saw that this is approximated by a train of impulses which has this additional modulation minus 1 to the k. Okay. So we looked at this signal. This essentially has, this can be written as a difference between two impulse trains which are delayed. So it has 2x the amplitude at odd harmonics and 0 at even harmonics, okay, of 1 by T naught, because when you separate it out, each of them has a period of T naught. Okay. So now we want to get the spectrum of this. We know the following. The discrete time signal tau d has a spectrum which spans from minus half to half. Okay. It has something. I mean, this is, okay, it's a function of the normalized frequency. And of course, like I always said, you can use the integral of this as a sanity check. Now, if you plot it as a function of absolute frequency f, it will have basically a spectral density. Let's see, this is now this will be okay. So this one, when it modulates an impulse train, that impulse train will have a spectrum. What was that? It was basically 1 by f naught, 1 by T naught times S tau d of nu times, f by f naught, right? F by f naught. Okay. So now if you look at this signal, this will have a spectral density that is okay, and if I express it as in terms of this one, right, S tau of f, I will essentially get one more f naught. Okay, is this correct? So you have an f naught here and you have another f naught from this. Basically, this is what I want. This is f naught times S tau of f times f naught. Okay. So this is what we'll have. This is only for one of the impulse trains. Okay. Now, if you want the spectral density of this, by the way, this will be the copy around DC, right? So the actual spectrum will be, there will be copies around every f naught. Okay. So now this is what we want. As I said, this part of it, where is that? This one has the same spectrum as an impulse train with a period of t naught, but with double the amplitude at even harmonics and odd harmonics and 0 at even harmonics. Okay. So essentially, this gets multiplied by 4, that is 2 square. The amplitude gets multiplied by 2, the spectral density gets multiplied by 4. Okay. And then you have 2Vp here, scaling. So what happens because of this? So this gets multiplied by 4Vp square. So if you write down the spectral density, you will get 16Vp square, f naught square, summation of this only for odd harmonics. Okay. Now it is proportional to Vp square, which makes sense because the jitter only influences the displacement of the edges, right? The amplitude is just proportional to the amplitude of the original signal. Okay. Whatever it is, it will get scaled by that. So that does make sense. So now you can write the spectrum of the jittery clock like this. It is the original clock plus the error signal, right? The original clock in a two-sided spectral density, it would have these. If it's one-sided, everything gets doubled, nothing changes, right? So what was the strength of this again? 4Vp square by pi square. Okay, and this was 4Vp square by 9 pi square and so on. Okay. Now around this, you will have a copy, and that copy is basically 16 Vp square. What is it? F naught square S tau of F minus F naught. Similarly, here you will have the same copy. This will be 16 Vp square F naught square S tau of F minus 3 F naught and so on. Okay. So essentially the square wave will have impulses at odd harmonics of the fundamental frequency, and then this jitter will have some sort of a spectrum around each of those harmonics. Is this okay? Now the interesting thing is that, let's say I look at this part, you can take any one of them, you will get the same result. Look at this part, and I normalize this to the strength of the tone itself. Okay, that is, I may normalize this to 1. That is, I divide by 4 Vp square by phi square. Now this becomes, what is it? 16 Vp square goes away as you expect, because both the signal and the error due to jitter are proportional to Vp. Okay, so it makes sense that the relative part is independent of Vp. So you will get 4 pi square f naught square S tau of f minus f naught. Okay. So S tau of f, or rather this is the time jitter, the actual displacement in absolute time units, and this is measured in seconds, right? And its spectrum is S tau of f. Now if you multiply this by f naught, what is this? This becomes dimensionless. Basically this is the normalized jitter, right, as a fraction of the period. Okay, so T naught is the period, and this f naught times tau of n says what fraction of it is the jitter. Okay, or it's known as the unit interval jitter, ui, and this is dimensionless, and you just put a unit of ui to say that it is basically normalized to the unit period. Okay, and obviously the spectral density of this is f naught square S tau of f. Okay. And what is this now? 2 by f naught tau of n. Phase. Basically this is the displacement as measured in radians. And this has a spectral density 4 pi square f naught square S tau of f. Okay. Is this okay? So what can you say about the spectral density of this jittery clock now? What is this? This normalized spectral density of the jittery clock. Essentially the phase noise spectrum or the phase jitter spectrum will appear around the tone. Okay? Is this fine? So an ideal, so if you do the calculation, you will get exactly the same thing even around this. But keep in mind here the frequency is 3f naught. So the phase of this signal would be 6 pi f naught times tau, right? The phase jitter corresponding to this frequency. So you will always get basically an impulse, and if you normalize it to that impulse, what you get will be the phase spectrum. Okay? Spectral density of phase jitter. So I'll show only the fundamental components. If that is normalized to 1, okay, this is an ideal periodic signal. A jittery signal, a real jittery signal will have a spectrum which is approximately like this. It will have that 1, and in addition to that you have the spectrum. And what is this? This is basically the spectral density of phase error, the spectral density of phase jitter translated to that frequency. Okay? So the phase itself will have, I mean, this whole thing, this is basically S phi of f, right? Is this okay? And this S phi of f, by the way, this, let's say, is S phi of f. This is the two-sided spectral density of the phase. Okay. And that gets translated to wherever the tones are. Okay. So if it's a sinusoidal signal, it turns out it simply comes to one frequency, and if it's a non-sinusoidal signal, it will have harmonics also, and this phase jitter will get translated to those frequencies. Okay. To go from time jitter to phase jitter, you have to multiply by 2 pi times that frequency. Is this okay? No. You normalize it to itself. So you normalize it to its own tone. Okay. So then you will get 9 times higher. But remember, the same time jitter corresponds to 3 times higher phase jitter at that frequency. Okay. So the phase jitter at that frequency for the same time jitter is 9 times higher. I mean spectrum wise. Okay. So you normalize it to, let's say you are only looking at this, you will get 9 times higher relative number. That is because the same time jitter corresponds to 3 times higher phase at that frequency. Okay. No, I didn't do that. I have not marked that impulse at all. So. No, then you would not mark it as one, right? Because then it will not be a square wave. Yeah. Is it okay? So this is basically what you will see. Now this is important because you will be given this phase spectral density. This is known as phase noise, and there are some conventions here which also have to be taken care of. This is phase noise, and this is a specification that is normally given with any clock. Okay, when you are given a clock, you can specify many things. Basically, you specify the phase noise spectrum, that is the frequency domain description of it, or you can specify the jitter variance in either absolute seconds or in radians or unit intervals. You just have to translate from one to the other. Okay. Now it turns out that what is normally specified as phase noise, you specify it only for positive frequencies. Okay. So let me show both of them. This is the two-sided spectral density of phi, the phase. Okay. Now, what is specified as phase noise? It's usually denoted by this L of f is just one side of this. Okay. This is not the one-sided spectral density of phase. Okay, then you should double the spectral density, but that's not what it is. You just specify one half of it. The practical consequence is when you want to specify what will be the phase variance. The variance of phase will be integral of integral of S phi. Okay. When phase noise is specified, you just have to multiply it by 2. It is specified only from 0 to infinity. You have to multiply this by 2. Okay. So these scaling factors are important while calculating things. Is this okay? So this is what is specified as phase noise. And if you see, if you like, let's say plug the clock that you have into a spectrum analyzer, the spectrum that you see, like we wrote, it will be like this. Of course, you will not see an impulse, you will see something like this. You will see some display like this, and then there will be a sharp peak, and then that. Okay, and this peak, assuming you have, this also depends on the bandwidth setting of the analyzer, but this denotes the peak power. I mean, not peak power, the power or the mean square value at that frequency f0. Okay, and then you have all these the spectral density around that. Now, if you look at the relative value, typically this is shown in dB, right? So if you just look at the difference in dB, right, that will be the phase noise. Okay, because essentially this this spectrum here, what you see on the side normalized to P0, that is phase noise. Okay, now when you see this difference on the log scale, that is basically like dividing by P0. Okay, and if you, let's say, let me show it on this side because it's shown only for positive frequencies. And let's say you look at some frequency which is f0 plus delta f. So this is sometimes written as L of delta f, and this delta f is called the offset. Okay, it's the same thing basically. Remember something, if you look at some frequency here, that will get translated to f0 plus that frequency. Okay, so that's why sometimes you specify it as phase noise at a particular offset frequency from the carrier or f0. Okay, so these are terms that you see, that's all. So you will see sometimes delta f simply means away from f0, because the way you typically measure it is you measure it on a spectrum analyzer, you measure the spectrum like this, you look at how far away from f0 you are and how far away from the power you are, that gives you the phase noise spectrum. Is this okay? So you can measure it. There are also specific phase noise analyzers that will detect the phase of the signal. I mean, they will have some ideal clock. Ideal meaning much cleaner than what you are expected to measure. I mean, most measurement instruments work like this, right? You want to measure something, and inside the instrument there will be a standard that is much better than what you are trying to measure in different ways, much more accurate. You compare the two and make a measurement. So that is one of the ways in which you measure phase noise. Then it will directly measure the phase and give you the spectrum. And in the case of spectrum analyzer, it just gives you the spectrum. Okay, and the whatever is around the carrier, you can interpret that as phase noise. Is this okay? So now typically this phase noise L of f will be specified as, this is the relative value, right? It is relative to the mean square value of the signal. Okay, so the units that are normally used are dBc per hertz. Okay, it's basically no unit, it's 1 by hertz, right? It's the relative value, but this dBc means this C refers to relative to the carrier. Okay, and you typically plot it on a log x and log y scale, and it may look like this. It may have some flat parts, and then it looks like that, and eventually it will have some floor, and at low frequencies it can have something like this, and so on. So if you look at the data sheet of any clock generator, it will have this type of behavior. And the reason for these things also, I won't get into the maybe I will show you the slopes also. So what can happen is that you can have basically a region where it is minus 30 dB per decade and minus 20 dB per decade and a flat one and so on. Okay, so these things are all possible, and then it can flatten out somewhere. So if you look at any clock generator or an oscillator, you will be given the phase noise spectrum. And once you have the phase noise spectrum, you can calculate the time jitter okay, or phase jitter or unit interval jitter. They're all scaled versions of each other. Only thing you have to remember is that this L of f is one side of the two-sided spectral density, so you have to multiply it by 2 before integrating. Okay. So there are some problems in the tutorial which relate to this. Okay. So for instance, you are given a picture like this. You are told that the relative value is something, and from that you can calculate the phase spectral density and the phase jitter and so on. Okay. And also the other way around. Is this okay? So these definitions again you have to know, because you want to know how much jitter there is eventually, right? The jitter variance determines the bit error also. Okay. Or you have to make sure that your bit period is longer than a certain value, which depends on the jitter variance. Otherwise you will get too many errors. So to calculate the jitter variance, you have to be able to find the spectral density of this phase noise and get the jitter variance. Okay. So in measurement you can use the spectrum analyzer. Now a spectrum analyzer is not the ideal method, because any noise, either amplitude noise or phase noise, everything will show up here. But we'll assume that close to this it is all phase noise. Or you can use the phase noise analyzer. From that you can get the phase noise plots and then integrate that to get the jitter. Okay. Any questions? So there are a couple of problems in the tutorial. I think once you go through the calculation, you will get used to this type of calculations. So this F here is the frequency of the phase. Okay. Now when you look at a clock with this phase, this entire spectrum gets translated to F0. Okay. So essentially this F will become F0 plus F. Okay. So this is the offset frequency. Sometimes, I mean, this is again convention, the notation is not always consistent. Sometimes you use delta F here, sometimes you use F. But this is the spectrum of the phase itself. But you don't see the phase directly, right? You see a periodic signal which has this phase. So each spectrum will have this spectrum translated to F0. Okay. So all the frequencies here get translated to F0. Is this fine? Any questions? So now we have looked at noise, the basics of noise. I think whatever we have done so far is good enough for us. Essentially, you need to know the variance of noise to find the bit error rate, both in the y direction, in which case you may have a voltage noise that is added to your signaling voltage, or in the x direction where you have a jitter added to your clock or the signal itself. Okay. The jitter can, I mean, I assume that the clock is jittery, but the data transitions also can have jitter, right? Because it is generated from some other clock in the transmitter. So that also will have the same effect. So you will need to know those things. And now we know how to, we know the very basics of random processes and the relations, I mean, how to describe a random signal, right? You can use the variance. We'll typically consider only zero mean, so that is okay. So the variance. And to see how rapidly or slowly it's varying, you can use the autocorrelation and spectral density. Most often you will have the power spectral density and you integrate that to get the variance, okay, and the standard deviation and so on. So we have noise in circuit components like MOS transistors and resistors, also bipolar transistors. From that you can calculate the voltage noise or current noise in any circuit. Similarly, you have phase noise with periodic signals. That is, signals are not exactly periodic. From there you can find the jitter variance from the spectrum of the phase noise. Any questions about anything we have done so far? Yeah, it is. So, meaning? No, I mean, it can be due to anything, but finally this random phase noise is due to thermal noise. The thermal noise will always be there, okay? You can try to minimize flicker noise, do whatever, but the thermal noise is fundamental. The only way to reduce it is by increasing the power dissipation. The same type of fundamental relationships you see for phase noise or the circuit noise. Okay. That's a very interesting thing you can try. So earlier I said that if you have a circuit, let's say this, something like this, okay. You have some noise here, okay. Let me call it output noise variance. Now, there may be many ways of reducing noise. One is to invent a new circuit that has less noise or less noise transfer functions and so on. Okay, that may or may not be possible. I mean, there may not be a more optimal circuit. Okay, so without getting into that kind of inventions, what is a circuit that will give me, let's say, half of this? So I want a circuit that will give me half of this noise variance. And let's say I don't want to do anything too intelligent, because I mean I can't rely on suddenly being able to invent a new circuit, but I want to just like modify the circuit to get half the noise. What can I do? Huh? So I can double the capacitor alone. I mean, I don't want to change the function of the circuit, right? What should I do? Huh? R and C both, that's it? And the MOSFET. I mean, there are three components. What is? So essentially what you do is, this is known as circuit scaling, which you will see more of, I think, in analog IC design. So you take two copies of the circuit and connect the corresponding nodes together. Okay. Anytime you do this, so imagine your circuit which is modeled by equivalent current noise sources, right? That we can do for both MOS transistors and resistors. What happens when you put two of these together? What happens to the spectral density of that effective current? You will have two current sources in parallel. So what happens to the spectral density? Why? The total current spectral density, what happens? It becomes 4 times. Why? 2 times. 2 times. The two are uncorrelated. For instance, I mean, you can directly get it from the noise spectral density of R by 2. But wherever you have, these two currents are uncorrelated, right? Noise currents. So whatever spectral density this has, if you make two copies, the spectral density becomes 2 times higher, the current noise spectral density. Now what happens to the impedance level at each node when you put two circuits in parallel? Half. So what happens to the voltages? It is current noise spectral density by something related to the square of the impedance, right? So it becomes half. So when you put two circuits in parallel, node by node, all the voltage noise variance or spectral density becomes half of what it was before. This is some very fundamental thing, okay. This is not related to any specific circuit. With any circuit this happens. So now all you have to do is, you see, this is known as impedance scaling, okay. So to have lower noise, you should have lower impedance levels. Instead of R, you have R by 2, and instead of a MOS transistor of width W, you should have 2W, and this, okay. This you may have to do because your initial design many times do not satisfy the noise specifications. You simply have to scale the circuit so that it works, okay. I mean, if you are able to invent a new circuit, that's fine, but here I am talking about when you have many parts of a circuit. Let's say this part is contributing too much noise and some other part is contributing very negligible fraction of the noise. what you may be able to do is scale up this part of the, or basically scale the part of this part of the circuit so that it contributes less. The other one, it was contributing, let's say, only 1%. Maybe you can actually scale it down so that it contributes more. Its contribution increases, but in the overall contribution, it may go from 1% to 2%. It's not a big deal. Okay. So this scaling is very important, and when you are optimizing circuits, this is something that you have to do. Yeah. No, I don't know which book does this. Now, variance and spectral density are completely different things. Yeah, I don't know. I think that's not necessary. Yeah, then you'll have to denote that as a function of frequency or something. Yeah, I mean the notation may be different, but the two quantities are of course quite different. Okay. So now what is the price that you pay when you do this? Area is fine, but power dissipation, right? The power is the important thing. Of course, the area also increases. So basically this, you're not getting something for free. You will have half the noise variance or noise spectral density at twice the power. So if you look at power dissipation, it will always be proportional to the signal to noise ratio. This is again some fundamental relationship. Okay. When I say half the noise, it's the mean square value of the power, and 2x the power. Okay. So now you can try this for yourself. What is the noise spectral density of resistor's noise current? 4 kT by R, and for the transistor 8 by 3 kT GM. Okay. So looking at these expressions, what else is there that you could change to reduce the noise by half? Temperature, right? You can cool down the circuit and you will get less noise. And by the way, this is done sometimes when you absolutely want very little noise in the circuits that are used for radio astronomy and so on, right? Where you are receiving really weak signals from probably outer space. So you want the noise added to be very small, so you can cool the circuits down. But how much power will that take? Let's say you use a refrigerator. So outside you have a temperature T, and inside you have a temperature T by 2, and you put your circuit here. The refrigerator needs some power. Okay, this circuit will take this power. So one way of reducing the noise was I keep it outside, and then I scale up the circuit by 2, it will take 2 times the power. So now if I put it in the refrigerator, I can maintain the same power dissipation, right? But the refrigerator itself needs some power. How much power will that be? What refrigerator? Huh? What's that? So what is the best refrigerator you know? Yeah, so you can use the Carnot refrigerator and calculate the power, see how much it comes out. Okay. So I think mostly you're probably familiar with the Carnot engine, where you get some mechanical output when it's operating between two temperatures. Here it's the other way around. You put in some input so that it transfers heat from the lower temperature to the higher temperature. It just works in reverse. The coefficients all remain the same. So now you can calculate it and see how this ideal refrigerator, this is of course an ideal refrigerator, real one will take a lot more power, but how the power in this compares to the circuit scaling. Okay. Any other questions? So now we can move on to the business of actually detecting the sign of the bit and so on. Okay. Basically this is all we need, right? We have the data coming in here and the clock is here. So this flip-flop or latch, whatever you want to call it, will determine the sign of the input at the clock edges. That's the idea. That's what is known as a decision slicer. Okay. So how do we make this? Yeah, so let's not go down to that kind of low level description. So let's say you had essentially we typically model all our circuits with control sources, right? So imagine that you have the MOS transistor is a voltage controlled current source. So you had voltage controlled current sources and some other components. How would you make something that takes a small signal and determines the sign? What could you do? What do you have to do? I mean, if you have a small signal and you want to determine the sign, what is the first thing you would do? Huh? Comparator, yeah. How do you make a comparator? Op amp. What? It's an amplifier, right? You basically need to make an amplifier. Okay. So, and if you amplify it by a large enough number, then it will go and saturate to the rails and it will become it will basically give you the sign of the output. Okay. So you don't want to use an op amp as a comparator, but anyway. So how do you make an amplifier? What is the model for an amplifier that you use? So it's basically the amplifiers that you know are essentially some voltage controlled current source loaded by a resistor, and there will always be some parasitic capacitor. This is very important because every MOS transistor comes with a parasitic capacitance at its input and its output. Let's now first consider only the output, but it's always like that. Okay. So now the idea is this is the amplifier. By the way, I will replace this symbol with this voltage controlled current source, right? This is usually in circuit literature denoted with this symbol. It's basically an op amp with its MOS chopped off. Okay. So, right. So now let's try to make our amplifier with this, and the idea is here you have to give as much gain as possible to the signal. Okay. So that you can basically the input swing may be small, maybe you are getting only 10 millivolts of signal, but you have to determine the sign of that, meaning the output should be interpretable as a unambiguous digital signal, either 0 or 1. Okay. So that means that it has to go to either the upper supply rail or the lower supply rail. Okay. That's the idea. So that means you have to have a large gain. So let's say this is the signal, and sometimes I may not show both the inputs. I may just show something like this. This means that I have connected the input to the positive, the other input is connected to ground. Okay. And I load it with a resistor, and it always comes with some parasitic capacitor. Okay. Now imagine that I have an input Vi, and initially I will assume a constant input, that is an input that is not changing with time. Okay. Is this fine? So if I apply an input, a constant input or a step input, I mean this denotes that I am starting the process at this time. What happens to the output voltage? It will do this, sorry. It will do that and eventually reach basically this is GMR times Vi. Okay. So now the GMR times Vi, if it is close to the, when it gets close to the supply rails, I mean I am now assuming a linear equivalent circuit, when it reaches saturation it will just get saturated. Okay. Is this fine? So now if I want to detect like smaller and smaller signals, what do I have to do? Huh? What's that? I have to increase the gain. So how do I do that? Increase the GM. But let's say I put n times GM here, this also becomes n times C. So what happens then? How will the output change in this case if I, so one second. Oh, no, let's do this properly. Okay, so this is Vi. Okay. Now let's say initially I will draw it with GMR equals 2. Okay. So the output originally would have gone like this. Okay. Now please sketch what would happen if you increase both GM and C by a factor of 2. This will increase the gain by a factor of 2, right? Also, alternatively, you can simply increase R by a factor of 2. Let's assume that in this case, C does not change. Okay. So just sketch the outputs and we can continue the discussion from the next class. Okay. Just see what happens. This is to evaluate the trade-offs. It's not that easy to increase the gain, as you will see.